Hey everybody, this is the review for chapter 1 through 8. We've covered a lot of material, so I want to run through it real quick with everyone. Make sure that you know these topics, and if there's something you're not sure of, go back and watch one of our old videos or practice some old web assigns. Got to get yourself prepared for seeing all these topics that you haven't maybe seen in a while. So let's start at the beginning. We went back to chapter 1, and in chapter 1 we start with vectors versus scalars. Vectors having a magnitude and a direction, while scalars just tell you how much. We also put vectors in three-dimensional space in the IJK format. Remember, you have that on your hand at all time. You have the X direction, the Y direction, and the Z direction all right here on your hand, so you can kind of visualize where things are pointing. We broke vectors into components, and the point of breaking them into components was to solve for the magnitudes. We took vectors that were in multiple directions, broke them into their individual pieces, and then put them back to find the magnitude and the resulting vector. Some of the math that went along with that, you can see over here, we used the trig for finding pieces of a triangle, and we used Pythagorean's theorem to solve for those hypotenuses. In chapter 2, we moved into position, displacements, and how things actually move. We visualized it with motion diagrams and graphed. Lots and lots of graphs in chapter 2. So make sure you go back and look at position sloping to velocity, velocity sloping to acceleration, or more specifically, velocity being the derivative of position, acceleration being the derivative of velocity. And reversing that with calc, being able to do integration to take yourself back from acceleration to velocity to position. Remember, integration is finding the area under the curve, while derivative just a fancy name for slopes. Also in that, we derived these kinematic equations here. Those kinematic equations came from our data. We were able to pull that from the area of the graph or the slope of the graph and give ourselves ways to solve for velocities, distances, times, accelerations. Those variables you guys have used many, many times in this chapter and in other chapters. And then the last thing we talked about was free fall acceleration. With free fall acceleration, we know that A is going to be 9.8 meters per second squared, or you can use 10 if you were dealing with a multiple choice, or if a problem says just use 10 as a decent reference on Earth. All right, when we got into chapter 3 here, we were looking at 2- and 3-dimensional motion. So basically everything we talked about in chapter 1, we now wanted to do in 2 dimensions or 3 dimensions, which means that we had positions, which was our R vector. That could be in X, Y, Z plane. We could have that velocity move in any of those directions, and we could have our acceleration move in all those directions. Remembering there that I told you to keep each of your pieces and your components separate, so just focus on the X, the Y, or the Z for your position, get your derivatives for velocity, and your derivatives for acceleration. We took that then into relative motion, which relative motion was really just vector addition. Go back and watch things about cars moving towards each other or away from each other. You've got to put yourself in whatever frame of reference they ask about to deal with a relative motion problem. We also looked at the moose in a river and how the moose drifted because his velocity was in one direction and the river was in an opposite direction. That then took us into projectile motion, where we used all of our kinematics equations again, and we looked at that in 2 directions. We looked at projectiles in the X direction and the Y direction. The nice thing about projectiles is they are completely independent of each other. So as you move in the X direction, you're moving at nice constant velocity. You're just basically following your inertia. And that means when you're moving at constant motion, there is no acceleration. You don't have to worry about accelerating in the X, which makes your equations that much easier. In the Y direction, though, you do have to worry about the acceleration. The thing that makes us accelerate as a projectile is gravity. So use 9.8 for your accelerations when you're using your projectile motion. Also, one thing they like to trick you up on, as you have a projectile going through those arcs, when you reach the top, we all know that it stops, but it stops in the vertical direction. The horizontal direction continues the projectile through its path, so they like to maybe ask questions like that and trip you up. We also talked about uniform circular motion. And what that meant with uniform circular motion was going around a circle at a nice steady speed. So we talked about timing things going around circles. We talked about the frequency, how often you go around that circle. And we also talked about its tangential velocity, which means it's linear velocity tangent to the circle. When things want to leave circles, they leave in straight lines tangent to the circle. The equation for speed is just the distance around a circle, which comes out to 2 pi r, and we divide that by the time it takes you to go around a circle. And then we also talked about this idea of centripetal acceleration. When you go around bends, you are accelerating in towards the center of the circle. At that time, we didn't really talk about the reasons behind why you accelerate inwards. We just said the acceleration points inwards by doing some vector subtraction, and so showing VF minus VO gives us an acceleration inwards. So the equation for centripetal acceleration, derive that to be v squared over r. So if you know your velocity and you know your radius, you'll be able to figure out how quickly your direction changes as you go around that bend. Which brings us now to chapter 4. And in chapter 4 was the cause of all the motion we saw in the first 2 chapters, Newton's laws. So Newton had 3 laws here. The first one we all know off by heart. It's basically following inertia. Your body will do what it was last doing. So if it was resting or moving, it's going to keep doing one of those last 2 things. There is no acceleration during Newton's first law event. For second law, we said that the cause of you changing your motion now was an acceleration, so F equals ma. And third law says that if I push on one object, that object must push back on me with an equal and opposite force. So we ran through many examples there, but if you punch the wall is going to punch you back. The only equation we really pulled out of this section was that force equals mass times acceleration. And the big thing you want to focus on with F equals ma is that it is a net force. So you have to surround a problem, draw a free body diagram, and identify forces that are on that object. Once you know the net force will make that mass accelerate. So F equals ma. Weight was a force that we dealt with, which is your force of gravity. So it's really mass times the gravitational field strength of our planet, which happens to be 9.8 newtons per kilogram, which is also meters per second squared. So the acceleration we dealt with in projectiles is the gravitational field strength of our planet. Mass, remember, is just your kilograms. That is just how many atoms make up your body. Force diagrams, the whole point of drawing a free body diagram was to eliminate all the clutter, identify forces, find a net force. That net force will then help you solve for an acceleration. And once you have an acceleration, you can then use all the kinematics we used back in chapters 2 and 3. We talked about inclined planes and tilted axes. So when you tilt the axis, make sure you tilt your XY plane as well, so that you can have the normal force parallel to the plane, and you don't have to worry about any angled forces except for the force of gravity. In gravity, we've broken that force into many pieces. Be careful which side of the triangle you're dealing with when you're doing tilted planes. Atwood problems are really just connected masses. Those connected masses will accelerate as one. So when one mass accelerates around, there's a rope attached to it usually, over a pulley, over the bend, and as the whole system accelerates, both objects accelerate at the same rate. The tension is kind of the go-between that allows you to solve for the acceleration of the connected system. You can actually use F equals ma and look at the total force, see what force is making the system go, and divide that by its total mass, because all masses must move, and that will give you the acceleration of the system as well.